Before we begin, it's essential to state that the information provided in this presentation is for educational and informational purposes only. This is not career, financial, or investment advice. The fields of study, salary data, and job market trends discussed are based on historical data and publicly available information, and individual outcomes can vary significantly. You should always conduct your own thorough research and consult with qualified academic and career advisors before making any educational or professional decisions. The single biggest lie we've been told about a high-paying engineering career is that it has to start in a lecture hall on a sprawling university campus. We picture the late nights in the library, the expensive labs, the ivy-covered walls. But what if that picture is completely outdated? What if the key to unlocking a six-figure salary, a future-proof career, and the respect that comes with being an engineer isn't found on a campus, but right through the screen you're looking at now? The truth is, for a select few engineering disciplines, the online degree has gone from being a questionable alternative to a strategic, powerful, and often superior choice. But which ones? That's the million-dollar question, because choosing the wrong online program is like buying a ticket on the Titanic. It looks impressive, but it's headed for disaster. You pick a field with shrinking demand, and you'll graduate into a sea of competition. You choose a discipline that requires intense, hands-on lab work, and your online curriculum will feel like learning to swim by reading a book. You end up with a degree that hiring managers secretly look down on, and suddenly, you're stuck with tens of thousands of dollars in debt, and a resume that keeps getting shuffled to the bottom of the pile. The dream of becoming an engineer evaporates, and you're right back where you started, only poorer. This is the exact problem we are going to solve for you today. This isn't just another list. This is your roadmap. We've spent hundreds of hours analyzing Bureau of Labor Statistics data, scouring job postings from major U.S. companies, and talking to industry insiders to identify the top 5 fields of study for an online engineering degree in America right now. We're going to break down each field based on 4 critical factors. First, raw job demand. Are companies actually begging for people with these skills? Second, salary potential. What can you realistically expect to earn, not just starting out but 5 to 10 years into your career? Third, and this is the most important for us, online suitability. How well does the subject matter actually translate to a digital learning environment? And fourth, future-proofing. Is this a career that will be enhanced by artificial intelligence or replaced by it? By the end of this video, you will have a crystal clear understanding of which path is right for you. You'll know which degrees open the most doors and which ones are dead ends. You'll be armed with the knowledge to invest your time and money wisely, sidestepping the pitfalls that trap so many aspiring engineers. Think of this as your strategic briefing before you commit to one of the biggest decisions of your life. Because the world of engineering has fundamentally changed. The old gatekeepers are losing their power. It's no longer about where you learned but what you can do. The rise of powerful simulation software, remote collaboration tools, and project-based digital learning has created a new paradigm. For certain disciplines, what used to require a multi-million-dollar physical laboratory can now be replicated, and in some cases even improved upon with a high-end laptop and a solid internet connection. This isn't just about convenience. It's about a fundamental shift in how complex problems are solved. Modern engineering is increasingly about data, simulation, and systems thinking, skills that are honed in a digital environment. The engineer of tomorrow isn't necessarily the one who can physically turn a wrench. It's the one who can write the code that designs the robotic arm that turns a million wrenches with perfect precision. And that kind of thinking is nurtured online. But let's be brutally honest. This revolution doesn't apply to every field. If you want to be a chemical engineer, you need to be in a lab mixing real chemicals. If you want to be a petroleum engineer, you need hands-on experience with drilling equipment. Trying to learn those fields entirely online is a recipe for failure. It's why so many people are skeptical, and frankly, they have a right to be. The internet is littered with for-profit colleges offering low-quality engineering degrees that aren't accredited by the right bodies, like ABET, the Accreditation Board for Engineering and Technology. An unaccredited degree is basically a very expensive piece of paper. It's a red flag to any serious employer in the United States. That's why our list only considers programs in fields where you can obtain a legitimate, ABET-accredited degree, the gold standard that puts you on equal footing with graduates from MIT, Stanford, or Georgia Tech. The goal here isn't to get just any degree. It's to get the right degree, one that commands respect, opens doors to top-tier companies, and provides a return on your investment that can change your family's financial future. This is about making a strategic choice, not just a convenient one. It's about leveraging the flexibility of online education to leapfrog into a career that is intellectually stimulating, personally fulfilling, and financially rewarding. We're about to count down from number 5 to number 1, and each entry on this list represents a massive opportunity. These are the fields where the digital and physical worlds are colliding, creating unprecedented demand for a new kind of engineer, one who is agile, tech-savvy, and comfortable solving problems from anywhere in the world. These are the sweet spots, the disciplines where the curriculum is perfectly aligned with online delivery, and where employers are more interested in your portfolio of digital projects than the brick-and-mortar building where you supposedly learned. So, if you're feeling stuck, if you're working a job that doesn't challenge you, if you know you have the mind of a problem solver but the traditional four-year campus path just isn't an option for you, then pay close attention. The next few minutes could redefine what you thought was possible for your career. We're going to give you the data, the insights, and the clarity you need to make a confident decision. Forget the old rules. The new path to becoming a highly paid, in-demand engineer is here, and it starts with knowing exactly which door to walk through. Let's begin the countdown. The field coming in at number 5 is a powerhouse discipline that has quietly become one of the most vital and versatile engineering roles in modern industry. It's the backbone of everything from manufacturing and aerospace to energy and robotics, and its principles are so fundamental that it's often called the evergreen field of engineering. Yet, its adaptation to the online format has been nothing short of revolutionary, opening the door for thousands of people who never could have accessed it before. This is a field for the creators, the builders, the people who love to see their designs come to life in the physical world. And that field, our number 5 pick for an online engineering degree, is civil engineering. It's the oldest engineering discipline, the one that quite literally laid the foundation for every other field to follow. Think about your day so far. The clean water that came out of your faucet this morning? A triumph of civil engineering. The roads you drove on, the bridge you crossed, the office building or home you're in right now. All born from the minds of civil engineers. It is the art and science of shaping the world around us, of building the very framework of civilization itself. This isn't just about pouring concrete and laying bricks. It's about tackling humanity's biggest challenges. It's about designing systems that can withstand the fury of a hurricane, providing clean water to growing megacities, and creating transportation networks that connect millions of people seamlessly and safely. The story of civil engineering is the story of human ambition. It's written in the enduring stones of the Roman aqueducts, the audacious span of the Golden Gate Bridge, and the monumental scale of the Hoover Dam, a project that tamed a mighty river and brought life to the American Southwest during the Great Depression. But the challenges of today are just as grand. Modern civil engineers aren't just building bigger. They're building smarter and more sustainably. They're developing smart cities with integrated sensor networks to manage traffic flow and energy consumption. They're designing green infrastructure that uses natural systems to manage stormwater. They're retrofitting older structures to be more resilient to earthquakes and the effects of climate change. This is a field with a legacy, but its eyes are fixed firmly on the future. Now, the question that's probably on your mind is a big one. How do you possibly learn a discipline so rooted in the physical world through an online program? How do you test the tensile strength of steel or analyze soil composition from your home office? It's a valid concern, and the answer lies in the incredible power of modern simulation technology. The online civil engineering curriculum has been revolutionized by software that was once the exclusive domain of top-tier architectural and engineering firms. We're talking about tools like AutoCAD, Civil 3D, and Revit. These aren't just digital drafting tables. They are profoundly powerful building information modeling, or BIM platforms. When you use BIM software, you aren't just drawing a two-dimensional plan of a bridge. You are building a three-dimensional, data-rich digital twin of that bridge. Every single component, from the largest support pylon down to the individual nuts and bolts, exists as a virtual object with real-world properties. You can assign it the material properties of reinforced concrete or structural steel. You can then run incredibly complex simulations. You can subject your virtual bridge to a 100-year flood, a Category 5 hurricane, or a massive earthquake, and watch in real time how the structure responds. You can analyze stress points, identify potential failures, and refine your design iteratively, all before a single piece of earth is moved. These virtual labs provide a level of analysis and experimentation that can, in many ways, surpass what's possible in a traditional physical lab. You can test a dozen different designs in an afternoon, something that would be physically and financially impossible in the real world. Many programs also integrate augmented and virtual reality, allowing you to walk through your designs at full scale, giving you a spatial understanding that was previously unimaginable. Of course, some things still require a hands-on approach. That's why many of the best online programs are technically hybrid. They might require students to attend a 1 or 2 week intensive lab session on campus during the summer, where they get to do the concrete mixing, soil testing, and materials analysis in person. Others build partnerships that allow students to complete lab requirements at a local community college or partner university, and the internship or co-op remains a cornerstone of the degree, giving you that critical real-world experience on an actual construction site or in a design firm. So, once you have this degree, what can you do with it? The career paths are as vast and varied as the infrastructure that surrounds us. You could specialize in structural engineering, becoming the mastermind behind the skeletons of skyscrapers, stadiums, and bridges. You are the one who ensures these colossal structures can defy gravity and stand for centuries. Or maybe you're drawn to geotechnical engineering, the fascinating science of the Earth itself. You'd analyze soil and rock to design stable foundations for everything from a single-family home to a massive dam. Or you might design the tunnels that run beneath our cities. Perhaps you're passionate about flow and movement. As a transportation engineer, you'd be the grand choreographer of motion, designing efficient and safe highway systems, airport layouts, and public transit networks. You'd use complex modeling to predict traffic patterns and reduce congestion, making life better for an entire metropolitan area. Then there's environmental engineering, a specialization that often falls under the civil umbrella. Here, you are the protector of our most vital resources. You'll design water treatment plants, waste management systems, and air pollution control facilities. You'll work on land remediation projects, cleaning up contaminated sites and restoring ecosystems. Finally, you could pursue construction management, where you are the field general, the one who takes the blueprints and turns them into a physical reality. You manage the budget, the schedule, and the teams of people on massive projects, ensuring everything is built to specification on time and safely. The demand for these skills is consistently strong. As you can imagine, the nation's infrastructure is in a constant state of evolution. Old bridges need to be repaired or replaced, water systems need upgrading to serve growing populations, and new transportation solutions are needed to meet the demands of the 21st century. According to historical data from the U.S. Bureau of Labor Statistics, the field of civil engineering has shown stable employment trends. While salary potential can vary significantly based on location, specialization, and years of experience, the median pay for civil engineers has historically been well above the national average for all occupations, reflecting the high level of skill and responsibility the job entails. It's a career path that has historically offered not just financial stability, but immense job satisfaction. There's a profound sense of purpose that comes from looking at a towering skyscraper or a bustling airport and knowing you played a key role in its creation. So, who is the ideal candidate for an online civil engineering degree? This field is for the practical visionary. It's for the person who is fascinated by how things work on a grand scale. You need to be meticulous, detail-oriented, and have a strong aptitude for physics and mathematics. But you also need to be a creative problem solver and a great communicator, able to coordinate with architects, city planners, and construction crews. It's for the person who can look at an empty field and see not just a building, but a community hub. It's for the person who gets a deep sense of satisfaction from creating things that are tangible, useful, and built to last. We've explored the world of the tangible, the concrete and steel that form the physical backbone of our society. But what about the invisible force that powers it all? The silent, crackling energy that flows through the veins of our modern world, lighting our homes, running our computers, and connecting us across the globe. That brings us to our number 4 field, a discipline that deals with a force you can't see, but can't live without. Electrical engineering. This is the art and science of harnessing electricity, the fundamental currency of modern technology. Every time you flip a switch, tap your phone screen, or ask a smart speaker for the weather, you are interacting with a system designed at its core by an electrical engineer. It is a field built on invisible forces, electrons dancing through copper wires, electromagnetic waves carrying data through the air, and the logical symphony of ones and zeros that form the basis of all digital information. Now you might be thinking, hold on, electrical engineering? That sounds incredibly hands-on. How can you possibly learn that online? Don't you need labs filled with oscilloscopes, soldering irons, and breadboards? And that is a perfectly valid question. 10, maybe 15 years ago, the answer would have been a firm no. But the game has changed, and the reason it has changed can be summed up in one word: simulation. The power of an online electrical engineering program lies in its mastery of sophisticated simulation software. Industry-standard tools like MATLAB, Simulink, and SPICE aren't just educational toys. They are the very same platforms used by professional engineers at companies like Intel, Qualcomm, and Texas Instruments. These virtual environments allow you to design, build, and test incredibly complex circuits and systems on your computer. You can construct a digital signal processor, model the power grid of a small city, or design an antenna for a satellite, all before a single physical component is ever touched. You can push systems to their breaking point, run thousands of diagnostic tests in minutes, and visualize the flow of current in a way that's impossible to see in a real-world lab. This digital-first approach not only makes a high-quality education accessible from anywhere, but it also develops a skill set in modeling and simulation that is becoming increasingly critical in the modern engineering workforce. So, what does the journey through an online electrical engineering degree actually look like? It begins with the bedrock principles. You'll start with circuit analysis, learning the fundamental laws that govern the flow of electricity. Think of it as learning the grammar of the language of electrons. From there, you'll move into the two great pillars of the field: analog and digital electronics. In analog, you'll study the continuous, wave-like nature of signals, learning how to build amplifiers and filters that are the heart of audio equipment and radio receivers. In digital, you'll enter the world of binary, the ones and zeros. You'll learn how to design logic gates, the microscopic decision makers that, when combined by the millions, form the microprocessors that power our entire digital world. As you advance, the curriculum branches into even more fascinating territories. You'll dive into electromagnetics, the physics behind everything from antennas to MRI machines, studying the invisible fields that carry our Wi-Fi signals and enable wireless charging. You'll explore control systems, the brains behind the brawn. This is the discipline that allows a drone to hold its position in a gust of wind, a car's cruise control to maintain a steady speed up a hill, and a factory robot to perform a task with pinpoint precision. And you'll master signal processing, the art of extracting meaningful information from raw data. This is the magic that allows your phone to distinguish your voice from background noise, that lets Spotify recommend a new song you'll love, and that enables a satellite to send back a clear image of a distant galaxy. Upon graduation, the paths that open up are as diverse as the field itself. One of the most critical and enduring specializations is in power systems. Electrical engineers in this area are the custodians of our nation's power grid. They design and maintain the massive generators, transformers, and transmission lines that keep our lights on. With the massive shift towards renewable energy, this field is undergoing a revolution, creating a huge demand for engineers who can integrate solar, wind, and battery storage into an aging grid, making it smarter, more resilient, and more sustainable. Then there's the world of microelectronics. These are the architects of the infinitesimal. They design the silicon chips, the microprocessors and memory, that are the brains of every electronic device on the planet. This field is at the forefront of technological advancement, constantly pushing the boundaries of what's possible by cramming more and more transistors onto a tiny piece of silicon. With recent global supply chain issues and a major push to bring semiconductor manufacturing back to the United States, the demand for skilled microelectronics engineers is incredibly high. If communication is your passion, the telecommunications sector is calling. These are the engineers who design the systems that connect us all. They work on the cellular networks that bring 5G and soon 6G to our phones. They develop the fiber optic systems that carry internet data at the speed of light under our oceans. And they design the satellite constellations that aim to bring high-speed internet to every corner of the globe. In a world that is more connected than ever, their work is the invisible backbone of modern society. In terms of career outlook, the numbers are compelling. According to the U.S. Bureau of Labor Statistics, the field of electrical engineering is projected to see steady growth over the next decade. The median pay for electrical engineers is consistently in the six-figure range, reflecting the high level of skill and critical importance of their work. This isn't just a job, it's a foundational career with a direct impact on virtually every sector of the economy, from healthcare and aerospace to consumer electronics and national defense. The ideal candidate for an online electrical engineering degree is someone driven by a deep curiosity about how things really work. You're not just content that your phone can stream video, you want to understand the physics of the radio waves that carry the signal, the design of the chip that decodes it, and the circuitry that powers the screen that displays it. You are a problem solver who enjoys abstract thinking and mathematics, seeing them not as academic hurdles, but as powerful tools for shaping the physical world. Electrical engineering is about mastering the abstract, the invisible forces that animate our technology. But all of those electrons, all of that code, and all of those signals are ultimately in service of a physical reality. They need a body, a chassis, a structure to inhabit. They need machines to move, systems to cool, and structures to withstand the stresses of the real world. That brings us to our number 3 field, a discipline that takes the theoretical and gives it form, function, and tangible moving parts. Mechanical engineering. It's often called the mother of all engineering for a reason. If it moves, uses energy, or is a physical product, a mechanical engineer was likely involved in its creation. This is the discipline that designs, analyzes, manufactures, and maintains mechanical systems. Think about the engine in your car, the landing gear on an airplane, the air conditioning system in your office, the robotic arm on an assembly line, or the tiny gears inside a wristwatch. All of it falls under the vast, versatile umbrella of mechanical engineering. At its core, it's the application of physics and materials science. You'll dive deep into 3 foundational pillars. First, there's mechanics, which is the study of forces in motion. This breaks down into statics, analyzing things that don't move like the trusses of a bridge, and dynamics, the science of things in motion like the suspension of a mountain bike absorbing a shock. Second, you have thermodynamics, the study of energy, heat, and work. This is the science that powers our world, from the combustion in a jet engine to the efficiency of a power plant, to the simple act of a refrigerator keeping your food cold. And third, there's fluid mechanics, which governs how liquids and gases flow. Essential for designing everything from the aerodynamic shell of a high-speed train to the network of pipes that deliver clean water to your home. Now, the big question, how on earth do you study something so hands-on, so physical through a computer screen? It seems counterintuitive, right? You can't exactly build a car engine in your living room for a final project. But this is where modern technology has completely revolutionized engineering education. The first game changer is simulation software. In a traditional program, you might spend a few hours in a physical wind tunnel. In an online program, you can use computational fluid dynamics, or CFD, software to run hundreds of virtual tests on a wing design, tweaking variables and seeing results instantly. You'll use computer-aided design, or CAD, to build intricate 3D models of machines, and finite element analysis, or FEA, to digitally stress test a virtual beam until it breaks, all without ever touching a piece of metal. These software suites are the exact same tools used by companies like SpaceX, Tesla, and Boeing. Online students often become more proficient in these digital tools than their on-campus counterparts because it's their primary way of interacting with the material. The second innovation is the rise of at-home lab kits. Top-tier online programs have solved the hands-on problem by mailing sophisticated kits directly to their students. You might receive a box with microcontrollers, sensors, and motors to build and program a small robot. You could get a materials science kit to test the properties of different polymers, or a miniature heat pump to conduct thermodynamics experiments on your desk. These kits, combined with virtual lab software, allow you to collect real data and gain that crucial hands-on intuition that is so vital for an engineer, all while maintaining the flexibility of remote learning. This combination of powerful simulation and hands-on home kits makes mechanical engineering an incredibly viable and effective field for online study. It's a pathway for the person working as a technician on a factory floor who wants to start designing the machines they operate. It's for the veteran with the knack for mechanics who wants to turn that skill into a professional career. And the career possibilities? They are almost limitless. This is perhaps the broadest of all engineering disciplines. A degree in mechanical engineering doesn't pigeonhole you into one industry. It gives you a master key that can unlock doors in dozens of them. You could be in aerospace, designing more efficient jet engines or lightweight satellite components. You could be in the automotive industry, working on the next generation of electric vehicle battery cooling systems or pioneering autonomous driving hardware. You could go into robotics and automation, creating the systems that build our products and explore other planets. There's the energy sector, designing massive wind turbines or improving the efficiency of solar power plants. There's the biomedical field, where you could develop advanced prosthetics or life-saving surgical devices. Even the world of consumer electronics needs mechanical engineers to figure out the thermal management for powerful processors and design the durable, sleek casings for our phones and laptops. According to the U.S. Bureau of Labor Statistics, the field shows stable growth, and the earning potential is significant, reflecting the fundamental need for these skills across the entire economy. A mechanical engineer's value lies in their ability to solve real-world, physical problems. Let's imagine a person named Alex. 4 years, Alex worked as a skilled HVAC technician. He was brilliant at troubleshooting complex heating and cooling systems in commercial buildings. He understood the practical side, the compressors, the ductwork, the refrigerants better than anyone. But he hit a ceiling. He saw the design flaws in the systems he was installing, but didn't have the credentials to be in the room where those designs were created. He wanted to be the one engineering better, more efficient systems, not just installing them. But quitting his job to go back to school for 4 years wasn't an option. He had a mortgage and a family to support. Then he found an accredited online mechanical engineering program. The transition was intense. Nights were spent wrestling with differential equations and the laws of thermodynamics. But something incredible started to happen. The abstract theories he was learning in his virtual lectures began to connect with the decade of hands-on experience he already had. When his class studied heat exchangers, he wasn't just looking at diagrams. He was picturing the hundreds he had personally serviced. For his capstone project, he used CAD and CFD software to design and simulate a novel geothermal heating system for commercial buildings, a project inspired by the inefficiencies he had witnessed firsthand in his job. He never set foot on a physical campus, but he collaborated with a team of students from 3 different time zones, presenting their final project to a panel of professors and industry professionals over a video conference. Upon graduation, Alex's resume was a powerful combination of proven, hands-on expertise and a rigorous engineering degree. He didn't just get a job. He was hired by a leading sustainable infrastructure firm as a systems design engineer, earning a salary that reflected his new qualifications and deep practical knowledge. He was now in the room where the decisions were made, using his unique background to create the next generation of energy-efficient buildings. Alex's story illustrates the potential pathway. Success in this field, especially online, requires a specific mindset. You need to have a strong aptitude for math and physics. There's no way around the calculus and the complex formulas. You must be a relentless problem solver, someone who sees a broken machine not as a nuisance, but as a puzzle to be solved. And you need spatial reasoning, the ability to look at a 2D drawing and visualize a complex 3D object in your mind. More than anything, you need the self-discipline to master this challenging curriculum on your own schedule. Mechanical engineering is the art of making the physical world work. It's about gears and levers, heat and pressure, force and flow. It's tangible. It's everywhere you look. But as our world becomes more interconnected, the machines we build are becoming smarter. The physical hardware is being fused with intelligent software. This deep integration of the physical and the digital brings us to our number 2 field of study, a discipline that lives at the very intersection of atoms and bits, hardware and code. Coming in at number 2 on our list is computer engineering. This isn't just about building faster PCs or designing the next smartphone. Computer engineering is the art and science of teaching silicon to think. It's the discipline that breathes life into inanimate objects, turning a collection of transistors and wires into a machine capable of calculation, communication, and even creativity. If electrical engineering forges the physical body of a machine, and computer science writes the consciousness, then computer engineering is the intricate nervous system that connects the two, translating abstract thought into physical action. It's the bridge between the world of pure logic and the world of physical electrons. So, how is it possible to study such a hands-on field, one that deals with tangible circuits and microchips, through an online degree? The answer lies in a powerful combination of simulation and sophisticated home lab kits. Decades ago, you needed a university lab filled with expensive oscilloscopes, logic analyzers, and power supplies to learn this trade. Today, the game has completely changed. An incredible amount of a computer engineer's work, especially in the design and verification stages, happens in the digital realm first. You'll use industry-standard software to design and simulate complex digital logic circuits before they're ever physically created. You'll write code in hardware description languages like Verilog or VHDL to describe the very architecture of a processor, then run it through a simulator to hunt for bugs, all from your laptop. But online programs know that's only half the story. You still need to get your hands dirty. That's why top-tier online computer engineering programs have perfected the lab-in-a-box concept. You'll be mailed kits containing microcontrollers like Arduinos or ESP32S, single-board computers like the Raspberry Pi, and most importantly, field-programmable gate arrays or FPGAs. These FPGAs are the real magic. They are blank slate computer chips that you can program at the hardware level to become anything you want. A simple calculator, a video game processor, or even a custom CPU of your own design. You're not just writing software to run on a chip, you are literally designing the chip itself. This gives you the hands-on practical experience that is absolutely critical, without ever needing to set foot on a physical campus. The curriculum of a computer engineering degree is a fascinating journey from the simple to the sublime. You'll start with the absolute bedrock, digital logic design. You'll learn about logic gates and/or not, the simple binary switches that, when combined by the millions, form the foundation of all modern computing. You'll learn how to combine these gates to create circuits that can store a bit of information or perform basic arithmetic. From there, you'll scale up to computer architecture. This is where you learn how to arrange those smaller building blocks into a functional computer. You'll study the anatomy of a central processing unit, or CPU, the brain of the operation. You'll dissect concepts like instruction sets, memory hierarchies, and pipelining, which are all clever techniques engineers use to make computers execute instructions faster and more efficiently. Then comes one of the most exciting and rapidly growing areas: embedded systems. An embedded system is a computer that's designed for a specific task and embedded within a larger device. Your car has dozens of them. Your microwave has one. Your smart thermostat, your fitness tracker, your television, they all run on embedded systems. In these courses, you'll learn to write highly efficient, low-level code, often in languages like C or C++, to directly control hardware. You'll learn how to read data from sensors, control motors, and manage power consumption, skills that are in monumentally high demand as we continue to build the Internet of Things. You'll also dive into operating systems, understanding the master software that manages all the hardware resources, and computer networks, learning the protocols and hardware that allow machines to communicate across the room or across the globe. So where does a degree in computer engineering lead? The career paths are as diverse as they are lucrative. You could become a hardware engineer at a company like Apple or Nvidia, designing the next generation of processors that will power our phones and AI data centers. You could be a firmware engineer, writing the low-level software that boots up a device and allows the operating system to take over. You could specialize as an embedded systems engineer at a company like Tesla, Bosch, or John Deere, developing the brains for self-driving cars, smart appliances, or autonomous tractors. Other roles include systems architect, validation engineer, or an FPGA/ASIC design engineer, working at semiconductor giants like Intel, AMD, or Qualcomm. The through line for all these roles is that you are the essential translator between the worlds of software and hardware. According to the U.S. Bureau of Labor Statistics, the field of computer hardware engineering showcases strong earning potential, reflecting the critical demand for these specialized skills in our tech-driven economy. The timing for pursuing this degree online has never been better, driven by three massive technological shifts. First is the explosion of the Internet of Things, or IoT. We are connecting billions of everyday objects to the Internet, from light bulbs to industrial sensors. Every single one of these things needs a small, power-efficient, and intelligent computer inside it, the exact kind of system a computer engineer is trained to design. Second is the rise of Edge AI. For years, artificial intelligence has lived in the cloud on massive servers. Now there's a huge push to move that intelligence to the edge, directly onto the device itself. This allows for real-time decision-making, like a security camera identifying an intruder without needing to send video to the cloud first, or a drone navigating a complex environment on its own. This requires specialized, low-power AI accelerator chips, a cutting-edge field where computer engineers are leading the charge. Finally, we are witnessing a fundamental shift in how we achieve performance gains in computing. For decades, Moore's law meant we could just shrink transistors to make chips faster. That era is slowing down. The future is about custom-designed, specialized hardware. Look at Apple's M-series chips. Their incredible performance comes from a system-on-a-chip approach where the CPU, GPU, AI engine, and memory are all tightly integrated and co-designed with the software. This holistic design philosophy is the very soul of computer engineering, and it's the future of the entire industry. Computer engineering is for the builder who wants to understand not just the code, but the silicon that executes it. It's for the problem solver who wants to work at the deepest level, where software and hardware become one. It is the discipline that builds the very fabric of our digital world, one logic gate at a time. It's a field that has fundamentally reshaped our reality, but it's still just the enabler. It builds the stage and the instruments. But what about the music itself? What is the universal language that runs on all this hardware? The abstract set of instructions that powers our apps, our financial markets, our social networks, and the entire digital economy. That brings us to our number one field of study, the discipline that represents the pure, unadulterated logic at the heart of the modern age. Computer science. This isn't just about learning to code. It's about learning the fundamental language of creation in the 21st century. If the Industrial Revolution was built on steel and steam, our modern revolution is built on silicon and software. An online degree in computer science isn't just a pathway to a job. It's an apprenticeship in modern-day alchemy, learning how to turn pure logic into tangible, world-changing tools. And for online learning, it is, without a doubt, the undisputed champion. Why? Because the very medium you're learning on, the computer, the network, the software, is also your subject matter. The classroom, the lab, and the final product all exist in the same digital space. You can learn the theory behind a distributed system in a morning lecture, and by the afternoon you can be deploying code to a cloud server from your own laptop, engaging in the exact same workflow as a senior engineer at a top tech company. This one-to-one mapping between the learning environment and the professional environment is something no other engineering discipline can fully replicate online. The demand for this skill set is almost difficult to comprehend. The U.S. Bureau of Labor Statistics consistently projects software development roles to be among the fastest-growing occupations in the country, with hundreds of thousands of new jobs expected over the next decade. This isn't a trend isolated to Silicon Valley. Every single industry is becoming a tech industry. Agriculture uses machine learning for crop optimization. Healthcare relies on sophisticated software for diagnostics and patient management. Finance is driven by algorithmic trading and secure digital transactions. The automotive industry is in a race to perfect autonomous driving. A degree in computer science doesn't pigeonhole you into one sector. It gives you an all-access pass to every sector. The potential for financial reward is, of course, a significant factor. Entry-level salaries for software engineers often surpass those in many other engineering fields, and the ceiling for growth is exceptionally high, with pathways leading to roles like principal engineer, solutions architect, or executive-level technology leadership. So, what does this journey of learning to speak the language of computers actually look like? It begins with the absolute fundamentals. You'll start with programming principles, often using a language like Python for its readability or Java for its structured, object-oriented approach. This is where you learn the grammar of coding: variables, loops, functions, and control structures. But more importantly, you learn to think like a programmer, breaking down complex problems into small, logical, manageable steps. This is computational thinking, and it's the single most valuable skill you'll acquire. From there, you dive into the bedrock of efficiency: data structures and algorithms. This is the difference between a clunky, slow application and a lightning-fast, elegant one. You'll learn how to organize information in the most efficient way possible, whether it's in a simple list or a complex tree, and how to write code that can sort, search, and process that information at scale. This isn't just abstract theory. It's the science behind why Google can search the entire internet in a fraction of a second. Once you have the foundations, the curriculum expands to the systems that make our digital world run. You'll study operating systems, peeling back the curtain on what actually happens when you click an icon. You'll understand how a computer manages memory, schedules tasks, and communicates with hardware. It's like going from being a driver to understanding exactly how the engine, transmission, and electronics all work together. You'll explore computer networks, demystifying the internet and learning about the protocols like TCP/IP that allow a message to travel from your phone, across the world, and to a server in milliseconds. You'll also get into database management, learning how massive companies like Amazon and Facebook store and retrieve petabytes of user data reliably and securely. But the real magic of a modern computer science degree lies in the specializations. This is where you get to aim your skills at the most exciting frontiers of technology. You could venture into artificial intelligence and machine learning, training neural networks to recognize patterns, make predictions, and power everything from your Netflix recommendations to medical image analysis. This is where you teach machines to learn from data, creating systems that can perform tasks previously thought to require human intelligence. Or perhaps you're drawn to the front lines of digital defense and cybersecurity. You'll learn about cryptography, network security, and ethical hacking, becoming a guardian of digital infrastructure, protecting critical systems from the ever-present threat of cyber attacks. In this field, the demand is so high that the unemployment rate is effectively zero. Maybe you're a builder at heart, in which case a specialization in software development is your calling. You could focus on web development, learning the front-end technologies that create beautiful user interfaces and the back-end systems that power them, becoming a full-stack developer capable of building an entire web application from scratch. Or you could focus on mobile development, building the next indispensable app for iOS or Android. And then there's the field of data science, which sits at the intersection of statistics, programming, and domain expertise. You'll learn to wrangle massive datasets, uncover hidden insights, and use that information to tell a story and drive critical business decisions. In an online CS program, the emphasis is relentlessly practical. Your homework isn't just problem sets, it's building projects. You'll create a web server, design a mobile app, build a machine learning model, or contribute to an open source project. Your GitHub profile, a repository of all the code you've written, becomes your living resume, a tangible portfolio that demonstrates your skills to potential employers far more effectively than a transcript ever could. And you won't be learning in a vacuum. Modern online programs utilize collaborative tools like Slack, Discord, and pair programming platforms to create a vibrant community where you work on team projects, debug code with classmates, and build the same remote collaboration skills that are now standard in the tech industry. Ultimately, an online degree in computer science is more than just an education. It's a direct on-ramp to the digital economy. It equips you with a powerful, versatile toolkit that is in high demand across every facet of modern life. The career paths are vast and varied: software engineer, cloud architect, DevOps engineer, machine learning specialist, security analyst, data scientist, or even a tech-savvy product manager. You're not just learning a trade. You're learning the principles of logic, problem-solving, and creation that will allow you to build the future. You gain the ability to look at a problem in the world and say, I can write a program to help solve that. That is a remarkable power to have. So we've now explored the landscape, from the tangible world of civil and mechanical engineering to the digital realm of electrical engineering and computer systems, and finally to the pure logic of computer science. We've covered our top 5 fields, each a powerhouse in its own right, each offering a unique pathway to a rewarding career through online education. The big question remains, however, with these incredible options on the table, how do you actually decide? How do you pick the one that's not just in high demand but is the absolute right fit for you? It's not just about looking at salary charts or job growth projections. It's about aligning your innate interests, your learning style, and your long-term ambitions with the specific demands of a discipline. Choosing the wrong path, even if it's a good one, can be a frustrating and expensive mistake. So, how do you make the right choice? What are the critical questions you need to ask yourself before you ever click apply? It starts not with a course catalog but with a mirror. The first and most important question isn't about job placement rates or starting salaries. It's about you. It's this: what kind of problems do you lose sleep over? What puzzles in the world grab you by the collar and refuse to let go? This isn't just a feel-good question. It's a diagnostic tool. Your obsession is your compass. If you find yourself endlessly fascinated by how we can build smarter, more resilient cities that withstand earthquakes and floods, that's the soul of a civil engineer speaking. If you're the person who looks at a chaotic factory floor or a hopelessly inefficient hospital check-in process and you can't stop mentally rearranging it, optimizing the flow and eliminating waste, you have the mind of an industrial engineer. Do you look at your smartphone and wonder not just about the app, but about the microscopic dance of electrons on the silicon chip that makes it all possible? The intricate logic gates, the power management, the very physics of computation? That's the call of the electrical or computer engineer. Or maybe it's the software itself. The elegant, invisible architecture of code that allows millions of people to connect, share, and create. If you dream in algorithms and data structures, you're already walking the path of a software engineer. Don't just ask what you're good at. Ask what you care about. Because the curriculum will get tough. The late nights will be long. And it's not the salary that will pull you through a brutal differential equations exam. It's the burning need to solve the problem that's on the other side of that degree. Once you know the what, you need to understand the how. The second question is, how is your brain wired? Engineering isn't a monolith. It's a spectrum of thinking styles. On one end, you have the pure systems thinkers. These are the people who see the world not as a collection of objects, but as a network of interconnected processes. They don't just see a car. They see a transportation system, a manufacturing supply chain, a fuel distribution network, and a traffic flow model. They think in flowcharts and feedback loops. They thrive on complexity and excel at optimizing the whole, not just the parts. This is the natural habitat of the industrial and systems engineer. On the other end of the spectrum, you have the deep focus, first principles thinkers. These are the minds that need to understand how things work at the most fundamental level. They're not satisfied knowing that a circuit works. They need to understand Maxwell's equations that govern the electromagnetic fields inside it. They don't just want to use a material. They want to understand its crystalline structure and stress-strain curve. This meticulous, analytical mindset is the bedrock of mechanical and electrical engineering. And then there's a third flavor, the visual spatial architect. The person who can mentally rotate a 3D object, who sees structures and forms in their mind's eye before they ever exist on paper. They think in blueprints, in CAD models, in the elegant lines of a bridge or the ergonomic curve of a product. This is a powerful trait in civil and mechanical design. None of these is better than the other, but they are profoundly different. Trying to force a systems thinking brain into a career that demands deep focus specialization can be a recipe for burnout. Understanding your natural cognitive style is like choosing the right tool for the job. You can hammer a screw, but it's not going to be pretty. This brings us to the third and perhaps most practical question you need to ask. Where do you fall on the spectrum from tangible to abstract? Imagine two engineers. One is Sarah, a mechanical engineer. She spends her days designing, building, and testing a new prosthetic hand. She can hold the prototypes. She can feel the texture of the materials. She can see the gears turn and the fingers grip. Her work is visceral, physical, and immediately real. Her failures are a cracked housing or a motor that overheats. Her successes are something a person can wear and use to pick up a cup of coffee. Now imagine Ben, a software engineer. He's designing the control algorithm for that same prosthetic hand. His entire world consists of lines of code on a screen. He works with data structures, object-oriented principles, and logical operators. His product is invisible, weightless. It's pure information. His failures are a bug that causes a millisecond of lag, or a memory leak that's only detectable after hours of operation. His success is an elegant, efficient, and flawless set of instructions that brings Sarah's physical creation to life. Both are brilliant. Both are essential. But their day-to-day reality is worlds apart. Do you crave the satisfaction of building something you can touch and point to? Or are you more excited by the challenge of architecting complex, invisible systems? Civil and mechanical engineering tend to live in the tangible world. Electrical, computer, and especially software engineering live in the abstract. Knowing which world you want to inhabit is critical. Finally, you have to zoom out. The fourth question is about your future 10-20 years down the line. What is your ultimate career ambition? Because an engineering degree isn't just a 4-year program. It's a launchpad. And different launchpads send you in different directions. Are you aiming for the C-suite? Do you see yourself as a future CTO, a VP of operations, or even a CEO? If so, a degree in industrial or systems engineering might offer a more direct path. These disciplines are often called the business school of engineering because they teach you to think in terms of efficiency, quality control, and supply chain management, the language of the boardroom. Do you dream of being a top-tier technical expert, a senior fellow, the go-to guru that everyone consults when the problems get impossibly hard? Then a deep specialization in electrical or mechanical engineering could be your ticket. These fields build the foundation for a career of profound technical mastery. Or is your dream more entrepreneurial? Do you want to build your own company from the ground up? While any engineering field can produce an entrepreneur, software and computer engineering have a distinct advantage in the modern economy. The ability to build a product with just a laptop and an internet connection creates unparalleled opportunities to innovate and launch a startup with relatively low overhead. And what if your goal is public service? To build the infrastructure that serves a community for generations? Civil engineering is the classic, noble path to literally building a better world. Think about the person you want to be in 2 decades: the leader, the expert, the innovator, or the builder. Your answer will illuminate which educational path provides the most direct route to that destination. Answering these 4 questions: what problems you want to solve, how your brain is wired, whether you prefer the tangible or the abstract, and what your long-term vision is, creates a powerful personal filter. It's a framework you can now use to evaluate any engineering discipline. It transforms you from a passive consumer of college brochures into an active, informed architect of your own future. You're no longer just looking for a good degree. You're looking for the right degree for you. This process ensures that your online education won't just be a series of classes, but a deliberate and meaningful step toward a career that aligns with your passions, your talents, and your deepest ambitions. It's the difference between buying a map and actually knowing your destination. Now that you have this framework, this personal blueprint for your decision, you're ready. You're ready to see how your answers align with the most powerful, in-demand, and future-proof online engineering degrees in America today. And we're starting with number 5, a field that is quietly reshaping the very fabric of our physical world, from the way you get your packages to the way hospitals save lives. At number 5, we have industrial and systems engineering. Now, this might not have the flashy reputation of building rockets or designing supercars, but don't let that fool you. This is the field of the puppet masters, the grand strategists of the modern world. Industrial engineers don't just ask, can we build it? They ask, can we build it better, faster, safer, and more efficiently? They are the architects of process, the masters of optimization. They look at a complex system, be it a factory, a hospital, or a global supply chain, and see not chaos but a puzzle to be solved. Think about the last thing you ordered online. You clicked a button and within a day or two, a package appeared at your door. That's not magic. It's a symphony of industrial engineering. An industrial engineer designed the layout of the massive fulfillment center, optimizing the path a worker or a robot takes to pick your item. They created the algorithms that determine the most efficient shipping route, factoring in thousands of variables in real time. They analyzed every single step, from inventory management to the final delivery, shaving off seconds and cents at each stage, which, when scaled to millions of packages, translates into billions of dollars and a seamless customer experience. Or consider a hospital emergency room. The chaotic environment you see on TV is what industrial engineers are hired to fix. They analyze patient flow from check-in to discharge to reduce wait times. They design inventory systems to ensure critical medical supplies are always in stock but never wasted. They create staffing schedules that match the number of doctors and nurses to predictable patient surges. They are literally saving lives by eliminating inefficiency. So, why is this an exceptional field for an online degree? Because modern industrial engineering is driven by data and simulation. It's less about being on a factory floor with a wrench and more about being in front of a computer with powerful software. Online programs excel at teaching these tools. You'll learn to use simulation software like Arena or AnyLogic to build virtual models of factories or supply chains and test changes without any real-world risk. You'll dive deep into statistics and data analytics, using languages like Python or R to find hidden patterns in complex datasets. You'll master project management principles and Six Sigma methodologies, all through a curriculum that can be accessed from anywhere. The collaborative projects you'll work on with classmates across the country mimic the global, distributed teams you'll likely join in your career. The career path for an industrial engineer is incredibly diverse. You're not tied to one industry. Companies in manufacturing, aerospace, healthcare, finance, tech, and retail all desperately need people who can streamline their operations. You could be a logistics manager for a company like FedEx, a process improvement specialist for a hospital network like Mayo Clinic, a quality assurance engineer for a car manufacturer, or a supply chain analyst for a tech giant like Apple. The Bureau of Labor Statistics has projected steady growth for this field, as the drive for efficiency and cost reduction is a constant in every industry. Historical salary data shows a strong earning potential, reflecting the immense value these professionals bring by saving companies millions. Industrial engineering is about optimizing complex physical systems. But what happens when the most complex, most critical systems are no longer physical but digital? This brings us to our number 4 pick, software engineering. If industrial engineers are the architects of the physical world's efficiency, software engineers are the architects of the digital universe itself. Every app on your phone, the website you're watching this on, the operating system running your computer, the complex trading algorithms on Wall Street, and the navigation system in your car, all of it is the product of software engineering. It's a field that has fundamentally reshaped society in just a few decades, and its importance is only accelerating. Let's talk about a company like Netflix. When you press play, you expect a movie to start instantly in high definition without buffering. That simple act is the tip of a colossal software engineering iceberg. Behind the scenes, thousands of engineers have built a system that can predict what you want to watch, store petabytes of video data around the world, and stream it seamlessly to over 200 million people at the same time, even during peak hours like a Friday night. They have to solve problems of immense scale. What happens if a server in Virginia goes down? The system has to automatically and instantly reroute traffic through a server in Ohio without you ever noticing a glitch. This isn't just coding. It's designing, building, and maintaining a resilient, scalable, and secure digital infrastructure that can withstand chaos. That is the essence of software engineering. Software engineering is arguably the field most naturally suited for an online degree. The entire profession lives on a computer. The tools you use to learn, code editors, compilers, version control systems like Git, and collaboration platforms like Slack, are the exact same tools you will use as a professional software engineer. In fact, many would argue that an online program prepares you better for the modern tech landscape, where remote work and distributed teams are the norm, not the exception. You learn to communicate effectively through digital channels, manage your time on complex projects without direct supervision, and collaborate on a shared code base with people you've never met in person. These aren't just secondary benefits, they are core marketable skills. Top online programs offer specializations in high-demand areas like artificial intelligence and machine learning, cybersecurity, cloud computing, or mobile development, ensuring your skills are on the cutting edge. The demand for skilled software engineers is, to put it mildly, astronomical. The Bureau of Labor Statistics consistently projects this field to be one of the fastest-growing occupations in the country. Nearly every company today is in some way a tech company, and they all need software engineers. You could be developing the next hit mobile game, building life-saving healthcare software, creating secure financial platforms for a bank, or working on the autonomous driving systems of the future. The job titles are varied: full-stack developer, DevOps engineer, site reliability engineer, data scientist, machine learning engineer. And because the demand so heavily outstrips the supply of top talent, compensation packages and career progression opportunities are among the most attractive in any industry. This field offers a clear path to building a career that is not only financially rewarding, but also puts you at the forefront of technological innovation, building the future one line of code at a time. But what if you want to build more than just the code? What if you want to build the very machine the code runs on? What if you want to understand the fundamental forces that power our entire digital civilization? From the microchip in your phone to the power grid that lights up your city. This brings us to our number one spot. The field that is, in many ways, the master key to all modern technology. It's the bedrock upon which software, robotics, and even modern mechanical systems are built. The number one field of study for an online engineering degree in America is electrical and computer engineering. Now, I know what some of you might be thinking. Electrical engineering? Online. How on earth do you learn about circuits and power systems without a physical lab? That is the single biggest misconception, and it's what holds so many brilliant minds back. We're going to shatter that myth today, because modern online programs have revolutionized this field, making it more accessible than ever. But first, let's understand why this degree holds the top spot. Think about your day so far. You were likely woken up by an alarm on your smartphone, a device designed by computer and electrical engineers. The coffee maker that started automatically, embedded systems, a core part of ECE. The car you drove, whether it's an EV packed with batteries and inverters or a gas car with a sophisticated engine control unit, is a masterpiece of electrical engineering. The Wi-Fi signal carrying this video to you, the servers in a data center processing it, the very screen you're watching it on, it is all, without exception, the domain of the electrical and computer engineer. It is the invisible magic that animates the modern world. While other engineers build the visible structures, the ECE professional builds the nervous system, the circulatory system, and the brain. This is the profound power of an electrical and computer engineering, or ECE degree. It's not one field. It's two woven together. The electrical side is the physics. It's the study of electricity, electromagnetism, and electronics. You learn how to generate power, how to transmit it, and how to use it in circuits. The computer side is the logic. It's the study of digital systems, computer architecture, and microprocessors. You learn how a computer thinks at the most fundamental level, right down to the ones and zeros flowing through logic gates. This duality is what makes ECE graduates so incredibly versatile and so consistently in demand. You're not just a hardware person or a software person. You are the bridge between both worlds. So let's tackle that big question, the hands-on labs. How does it work online? The answer is a two-pronged approach that is, for many students, even more effective than a traditional lab setting. First, you have industry-grade simulation software. Programs like Multisim, Spice, and MATLAB allow you to design, build, and test incredibly complex circuits and systems entirely in a virtual environment. You can push components to their breaking point, test scenarios that would be too expensive or dangerous in a real lab, and get instant feedback on your designs. You can build a virtual microprocessor or simulate an entire city's power grid, all from your laptop. But it doesn't stop there. The second and perhaps most exciting part is the at-home lab kit. Top-tier online universities will mail you a physical kit, often called an analog discovery kit or something similar. This isn't a toy. This is a portable electronics lab. Inside, you'll find a breadboard for building circuits, an oscilloscope, a waveform generator, a power supply, and a whole host of components like resistors, capacitors, and microcontrollers like the Arduino or Raspberry Pi. You follow along with video lectures, build real, physical circuits on your desk, and use the provided tools to measure voltage and current, just like you would in a campus lab. The difference is you get to keep the equipment, tinker with it 24/7, and build a deep, intuitive understanding that you can only get by actually doing. Once you have this foundational knowledge, the career paths that open up are staggering. The field of ECE is so vast, it's best to think of it in terms of its major specializations. First, there's power systems. These are the engineers who keep the lights on. They design and manage the massive infrastructure of power generation, transmission, and distribution. With the global push towards renewable energy, this field is undergoing a seismic shift. Power engineers are the ones figuring out how to integrate vast solar and wind farms into our aging grid, designing smart grids that are more efficient and resilient, and developing the battery storage technology that will power our future. This isn't just a job, it's a role in national security and environmental sustainability. Then you have microelectronics and semiconductor design. If power systems are the muscle of our world, microelectronics are the brain. This is the art and science of designing the computer chips, the processors, memory, and sensors that are in literally everything. Engineers in this specialization work at the nanoscale, arranging billions of transistors on a tiny sliver of silicon. They are the architects behind the chips that power Apple's iPhones, NVIDIA's GPUs for artificial intelligence, and the processors in next-generation vehicles. With recent global events highlighting the critical importance of semiconductor manufacturing, this field is experiencing a historic boom in the United States, with massive investment and soaring demand for talent. Next up is communications and signal processing. How does your cell phone talk to a tower miles away? How does GPS pinpoint your location from space? How does your smart speaker understand your voice commands? The answer is signal processing. Engineers in this area are masters of information. They design the algorithms and hardware for 5G and the upcoming 6G networks, develop the advanced radar systems used in aviation and autonomous vehicles, and create the technology that allows us to filter, analyze, and interpret data from the world around us, from medical MRIs to deep space radio telescopes. It's a field that blends deep mathematics with practical application, connecting our world one signal at a time. Finally, there's the specialization that gives the degree its second name, computer engineering, which often includes embedded systems. This is the ultimate fusion of hardware and software. While a computer science major writes software for a general-purpose computer, a computer engineer designs and builds the entire computing system for a specific task. Think about the complex web of sensors and controllers in a modern car, the flight computer in a drone, the life-sustaining electronics in a medical pacemaker, or the vast network of smart devices that make up the Internet of Things, IoT. Computer engineers are the ones who design the custom circuit boards, select the right microprocessors, and write the low-level firmware that makes these dedicated devices work flawlessly. They live at the thrilling intersection where code meets the physical world. The career outlook reflects this incredible breadth and importance. The U.S. Bureau of Labor Statistics projects steady growth for electrical and electronics engineers, with median pay well into the six figures. But that number just scratches the surface. Specialists in high-demand areas like RF engineering for communications or ASIC design for semiconductors can see compensation packages that are among the highest in the entire engineering profession. The demand is not a fleeting trend. It is woven into the fabric of our economic future. The electrification of transportation, the rollout of 5G, the explosion of IoT, and the strategic push to bring chip manufacturing back to American soil are all powerful long-term tailwinds driving demand for ECE talent for decades to come. An online degree in electrical and computer engineering is a ticket to the very heart of modern innovation. It's for the person who isn't satisfied just using the magic of technology, but feels a deep-seated need to understand how the spell is cast, right down to the last electron. And while computer engineering is about the brain and the nervous system of modern technology, there is one field that represents its skeleton, its muscle, and its heart. The one discipline that is so fundamental, so versatile, that it acts as a master key, capable of unlocking doors in nearly every industry imaginable. This brings us to our number 1 field of study for an online engineering degree in America. You might be expecting something like AI engineering or quantum systems, but the truth is, the most powerful choice is often the most foundational one, reimagined for the 21st century. The number 1 field is mechanical engineering. Now hold on. Before you click away thinking of greasy gears and old steam engines, let me reframe this for you. Forget the stereotypes. Today's mechanical engineering is about robotics, nanotechnology, sustainable energy, biomechanics, and aerospace systems. It is the discipline of creating motion, power, and form. If software is the ghost in the machine, mechanical engineering is the machine itself, and it is more sophisticated and in demand than ever before. Why is it number 1 for an online degree? Because the revolution in software has now come full circle to empower the design of the physical world. In the past, the knock against an online ME degree was the lack of hands-on lab work. But that argument is dissolving. Today, you'll spend your time in virtual labs running sophisticated simulations that were once only available to massive corporations. You'll use finite element analysis software to digitally stress test a bridge design until it breaks, without ever pouring a single ounce of concrete. You'll use computational fluid dynamics to perfect the aerodynamics of a race car, running thousands of virtual wind tunnel tests in a single afternoon. You'll master CAD software like SolidWorks or Fusion 360, the digital clay that allows you to sculpt anything from a new smartphone chassis to a prosthetic limb, and then 3D print a prototype from your own desk. The tools of the modern mechanical engineer are increasingly digital, making an online education not just viable, but in some ways more focused on the skills companies need right now. At its core, mechanical engineering is built on the pillars of physics. You'll master thermodynamics, the science of energy itself, how to harness it from a solar panel, how to use it efficiently in an electric vehicle's battery system, and how to manage its waste heat in a massive data center. You'll study fluid mechanics, understanding how air flows over a drone's propeller, or how life-saving medicine moves through a microscopic pump. You'll dive deep into materials science, learning why one specific titanium alloy is used for a jet engine turbine blade, while a new polymer composite is perfect for a lightweight bicycle frame. And you'll bring it all together in robotics and control systems, designing the intricate series of motors, sensors, and actuators that allow a surgical robot to perform a procedure with superhuman precision. But the true power of this degree lies in its unbelievable versatility. A mechanical engineering degree doesn't just prepare you for a job, it prepares you for a dozen different careers. You could start your career designing the landing gear for the next generation of reusable rockets at a company like SpaceX or Blue Origin. You could then pivot to the renewable energy sector, engineering more efficient and durable wind turbines to power our future. Feeling a call to help people more directly? You could join the biomedical field, developing cutting-edge prosthetic hands that can feel, or designing MRI machines that are quieter and more comfortable for patients. You could work for Apple or Google designing the thermal management systems that keep our devices from overheating, or for a car company like Rivian or Tesla, engineering the powertrain and suspension for a new electric truck. From the roller coasters at an amusement park to the HVAC systems that keep our hospitals safe, a mechanical engineer was there, solving the problem. It is the ultimate utility player of the engineering world. So as we look back on our list, a clear picture begins to emerge. It's not about which of these 5 fields is best. It's about understanding the incredible interconnected ecosystem they create. We started with software engineering, the architects of the digital world, writing the code that runs our lives. We moved to electrical engineering, the masters of the current, designing the circuits and power systems that bring that code to life. We then explored civil engineering, the builders of the modern stage upon which society functions, from our bridges to our water systems. We dove into computer engineering, the crucial bridge between the worlds of software and hardware, designing the processors and embedded systems that make our devices intelligent. And finally, we landed on mechanical engineering, the creators of the physical world, building the machines, the products, and the systems that all of this technology ultimately inhabits and controls. Think of it like building a self-driving car. The software engineer writes the navigation and decision-making algorithms. The electrical engineer designs the power distribution system, the sensors, and the communication networks. The computer engineer designs the specialized computer chip that processes all that sensor data in real time. The civil engineer designs the smart roads and charging infrastructure the car will use. And the mechanical engineer designs the car itself, the chassis, the suspension, the motors, the braking system, and the robotic components that actually turn the wheel. You can't have one without the others. They are all essential and they are all converging. So the final and most important question isn't which degree will be most successful? It's which set of problems are you most passionate about solving? That's how you choose. This is the framework you should use. First, apply the curiosity test. When you look at the world, what makes you stop and wonder, how does that work? Are you the person who looks at a skyscraper and wonders about the physics holding it up? That's the mind of a civil engineer. Do you see a complex app like Uber and immediately start thinking about the logic, the database, and the user interface? You're thinking like a software engineer. Do you open up an old radio just to see the circuit board, tracing the paths of electricity? That's the spark of an electrical or computer engineer. Or do you look at a robotic arm in a factory and obsess over the gears, the motors, and the sheer physical grace of its movement? You have the heart of a mechanical engineer. Follow your natural curiosity. It's the fuel that will get you through the late nights of studying. Second, use the impact lens. What kind of mark do you want to leave on the world? If you dream of building a more sustainable future, with green cities and clean energy, civil or mechanical engineering could be your path. If you're driven to connect people and information, to build the next social network or a revolutionary educational platform, software engineering is your calling. If you want to be on the front lines of technological advancement, creating smaller, faster, and more powerful electronics or the brains for artificial intelligence, electrical and computer engineering will put you right there. Don't just think about the job title. Think about the change you want to create. And finally, consider your personal grit factor. An online engineering degree is not easy. It requires immense self-discipline, proactive communication, and a genuine love for the subject. The beauty of online learning is its flexibility. But that flexibility requires you to be the master of your own schedule. Be honest with yourself about your ability to build a routine, to seek help when you need it, and to stay motivated when you're staring at a complex equation at 10 o'clock at night. The most successful online students are not necessarily the ones who are the most brilliant, but the ones who are the most resilient. Choosing to pursue an engineering degree online is a monumental decision. It's a commitment to becoming a problem solver, a builder, an innovator. It's a choice to join the ranks of people who don't just see the world as it is, but as it could be. Each of these 5 fields offers a unique path to becoming an architect of that future. So now I want to turn it over to you. Based on everything we've talked about, which of these fields ignites that spark of curiosity in you? And more importantly, what is one problem in the world, big or small, that you would want to solve with those skills? Let's fill the comments with the ambitions and ideas of the next generation of engineers. Share your vision, because the journey starts not with an application but with an answer to the question, what will you build?